All right, here in chapter 16, we're going to look at acid-base equilibrium. So now we're going to take this idea of equilibrium and apply it to acid-base reactions. So the first thing we're going to do is remember exactly what an acid is and what a base is. And this might be from quite a while ago, so let's see what we can remember. Okay, acids will have a sour taste, and they often will cause dyes to change color. Bases, in the most general sense of the term, often have bitter tastes, which actually is different than sour, okay, and will often feel slippery. There are a couple different definitions for acids and bases based on different points in history when people were defining them differently. We started with a little more general term here. We're going to look at an Arrhenius base. That's a last name. And those are when substances dissolved in water increase the OH minus concentration. That's what he called an Arrhenius base. An Arrhenius acid is when a substance dissolved in water increases the H plus concentration. So those are the first and our kind of general acid-base definitions. Now we're going to look at a Bronsted-Lowry acid-base definition, because the Arrhenius ones aren't really exactly what we want, because they only apply to aqueous solutions, and they're only dealing with H plus or OH minus. And there are way more different types of things that are acids and bases. They don't just have to be an aqueous solution. Okay, when we talk about a Bronsted-Lowry acid or base, we're talking about donating a proton to a substance or accepting a proton from a substance. And a Bronsted-Lowry acid, we are donating or donates a proton to a substance. Okay, again, no aqueous phase is needed. You could have gases. A Bronsted-Lowry base is we're going to have something that accepts a proton. And again, no aqueous phase is needed. When we talk about acids and bases, we also have another term. We have an H plus, which is often called a hydronium ion. It's the same thing as H3O plus. So if we had H3O plus or H plus, those are actually the same thing, because one of them has a water attached to it. You actually really find this in a solution and not that, but everybody knows it's this, so we kind of shorthand it right just to be H plus. That's really all we care about. Another thing you want to keep in mind here with Bronsted-Lowry acids and bases is that they work in pairs. You can't have one without the other, because I would then have nobody to transfer a proton to, or nobody to accept the proton. So you've got to have one and the other. Okay, you can have amphiprotic and amphoteric, which is when something acts as both a acid and a base. And our best example here is water. Water can act as either an acid or a base, depending on what it's dealing with. All right, so the first one we're going to look at here with these acid-base pairs are what we call conjugates. Okay, every acid has a conjugate base that is formed when the proton is removed, and then every base has a conjugate acid that's formed when we add the proton. So here's the example. If I have HX, so X is just some element. Okay, so that's my acid. Acids start with H. Okay, I'm going to add that to water. So water is going to be my base. Have my equilibrium. All right, since HX is the acid, I'm going to donate my proton, or donate the H plus. So this H is going to go over here. I'm going to end up with X minus, the leftover, plus H3O plus. My acid here in red lost its proton, okay, to the base. The base gained the proton, and now I have an extra one. Well, if we go the other direction, okay, H3O plus, the H3O plus lost its H to the HX, and I made HX. So in this case, this is the acid, and this is the base. You're going back to the left, okay? So we call these conjugate acid-base pairs. This is the acid, and this is my conjugate base. This is my acid on the right, so that would be considered a conjugate base if you go to the left. But we want to go to the right because we tend to look at things left to right. So this is my base, and this is the conjugate acid. They are pairs. The base gained the extra one, so when we go the other direction, it's going to lose it. Okay? Again, they always appear in pairs. So let's look at these strengths for these acids and bases. Okay? Some will donate protons better than others. Okay? Because again, we're talking about an acid as being able to donate the proton. So the more easily an acid loses the proton, the less easily its conjugate base accepts the proton, which is the reverse reaction. So the stronger the acid, the weaker the conjugate base, meaning that my reverse reaction will not happen. When we talk about a strong acid, remember, that means that it's going to really easily fall apart. It's really easily going to ionize. So a strong acid means I'm going to have a really weak conjugate base. That base on the right side is not going to want to recombine to make that acid on the other side. When we talk about a strong acid again, these are ones that completely transfer the proton. It's usually we talk about to water. Okay, the conjugate base has no tendency to gain the proton back from water, which means that it is a weaker base than water. Okay, my equilibrium lies far to the right. It's almost all original acid is a part, which means I'm pretty much all ions. Okay, so for example, if I have something like HCl, it's going to fall apart into H plus and Cl minus. I could also write that as a side note, and doing HCl plus water is going to yield H3O plus Cl minus. We just tend to ignore the water. Either way is fine. What this means here is that this HCl is pretty much all going to fall apart and go to the right. Here is my acid. There's the base. This lost, so here's my conjugate base. Here is my conjugate acid. The conjugate base right here, this Cl minus, does not want to gain or take that H plus back from water to make HCl. It's not going to happen. Cl minus here is too weak. It's very, very, very weak. It's not going to recombine and go the other way. Strong acids are almost, actually, instead of a double arrow, they're really a single arrow to the right. Okay, they rarely, really do not come back the other direction to the left. Okay, water is a stronger base and will keep those protons. All right, here's an example on the right there of that chart that shows that HCl is a very strong acid. Cl minus is a negligible base, meaning it's really not even a weak base. You get into a weak acid like HF, then F minus is a weak base, the opposite of it. Okay, if we talk about OH minus being a very negligible or small, very, 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 very weak base, O2, the other side, is a very strong one, or weak acid is a strong base. Okay, if I've got a very weak acid, you're going to have a very strong conjugate base. Okay, let's look at the examples here for weak acids. Okay, so weak acids only partially dissociate, which means that you have a mixture of acid molecules and ions. Okay, my conjugate base will remove protons from water. It is a stronger base than water now. My equilibrium lies far to the left. Okay, most of the original HA, the A being any acid, is present. Most of it, but not all. Okay, if something has negligible acidity, meaning it's not really an acid at all, okay, some molecules have hydrogens, but they're not an acid.